Today we're going to be continuing our discussion of graphing to specifically talk about how do you actually end up graphing equations using your knowledge of how substitution works in terms of evaluating algebraic expressions, and therefore how you can find ordered pairs to plot on the coordinate plane. So the first thing you want to kind of know is how do we even interpret an equation in terms of knowing if a point is supposed to work? Well, if a point exists on an equation, so this equation is depicting some sort of recipe that if you plug in any x, you can output any y, and any xy pair have to make this equation true. So if, for example, I wanted to check if the point 3, 4 were on this line, I would plug in y is equal to 3, and then everywhere I see an x, plug in a 3, so 3 times 3 minus 5. Y is equal to 9 minus 5. 9 minus 5 is 4. And indeed, that is on that line. Versus if I try to do a similar process and plug in, let's say, 4, 5, something I'm already predicting is probably not on the line. If I tried to plug that in the same way, so 3 times x, in this case x is 4, minus 5. 3 times 4 is 12, minus 5 is actually 7, not 5. So that means that point is not on the line. Versus 3, 4 is on the line. So with that in mind, keep in mind that the line's equation in this case is y equals 3x minus 5. Go ahead and check which of these points is on this line and which one is not. Some will be and some will not. So pause your video and then check in to compare your answers with what we get. Okay, so if we're going to plug in the first one, so we're plugging in 3 times negative 1 minus 5. 3 times negative 1 is negative 3. Negative 3 minus 5 is negative 8. So no, it does not match. Negative 8 is not equal to negative 6, so it is not on the line. Versus if I plug in negative 3, everywhere I see an x, I'm replacing it with my x value, in this case negative 3. 3 times negative 3 is negative 9. Minus 5 is negative 14, so that is also not on the line. Similarly, if I were to plug in positive 1, 3 times 1 is 3, minus 5 would get us negative 2, which is not the same thing as negative 1, so that's also not on the line. If I were to plug in 0, 3 times 0 is 0, minus 5, that is actually equal to that same y value, so we are good. That means yes, it does match, and yes, it is on the line. Now, as you can already see, literally guessing and checking every combination of points is simply not going to work. But this process that we really end up going through in the work column, that's what you're going to end up doing in order to plot equations. And what do I mean by that? Well, rather than predicting exactly what the xy pair should be ahead of time, go ahead and just set some potential x values that you're going to plug in for x and then see what y happens to come out. And then what you've really found is some sort of ordered pair. And you could do this with any equation, doesn't have to be linear, but right now we're focused on linear equations, so those usually end up just being x multiplied by something and then x added or subtracted to something. So with that in mind, let's just kind of walk through what that would look like. So for example, in this equation, y equals negative 2x plus 2. If you were to plug in negative 2, that means everywhere you see an x, you replace it with negative 2. Then you follow order of operations. The negative 2 times negative 2 is 4, plus 2 would give you 6, to give you a final order pair of negative 2, 6. And once you have these ordered pairs, you can go ahead and plot them on the coordinate plane to get your pattern. So for example, negative 2, 6, we go left 2, up 6. Negative 1, 4, we go left 1, up 4. 0, 2, we go left and right nothing, up 2. And you might already see the pattern of the line. But just in case, we're going to go ahead and plug in a couple other points and see if it follows the rest of the pattern. So go ahead and pause your video and try to plug in these last two suggested points, and then see if it forms a nice, beautiful straight line. So for these last 2 points, if I were to plug in positive 1, negative 2 times 1 is negative 2, plus 2 is going to give us a 0. So we just confirm there's the point 1, 0. Similarly, if I were to plug in positive 2, negative 2 times 2 is negative 4, plus 2 is going to get us negative 2. So we just confirm there's the point 2, negative 2. And then if I were to plot these points, we have 1, 0, 2, negative 2, and then we can connect them in a nice, beautiful straight line. Now you might be wondering, why did we pick these x values? There's no reason in particular. We were just kind to ourselves and picked relatively small x values that would be relatively easy to plug in, but ultimately you can choose to plug in whatever numbers float your boat, makes sense to you. The only thing that I would say is you probably want to pick x values that are on the coordinate plane you're supposed to be plotting on. So if, for example, I picked x is 20 over here, that would be kind of useless for the purposes of plotting this particular line on this particular pre-labeled coordinate plane. So I'd probably want to pick x values that were somewhere in between negative 16, it looks like, is over here, and positive 16 is over here. But as long as I stayed in between those, we're good. Now there are some very special types of coordinates that always occur on lines. In particular, these places where we cross the x and y axis, those have special names. In particular, the x-intercept and the y-intercept. So the y-intercept is the one that intercepts, that crosses your y-axis. It always takes the form of 0, some sort of y coordinate if it's going to be a y-intercept. And you want to keep in mind this visual when doing that, because it can seem somewhat counterintuitive that in order to find a y-intercept, that means that x is always 0. Similarly, if it's going to be an x-intercept that crosses the x-axis, and it's always going to take on the form of x, 0, because we are an x-intercept crossing that x-axis. So in that case, y is always equal to 0. The nicest way to try to identify them is visually, because you can see visually that an x-intercept crosses that x-axis, while a y-intercept is going to visually cross that y-axis, and then you label the points according to how you would normally label those coordinates. So go ahead and pause your video and see if you can identify the intercepts in each of these depictions. So for this first graph, we've got ourselves an intercept over here at negative 4, 0, and an intercept down here that occurs exactly halfway in between negative 8 and negative 12. So is at 0, negative 10. Negative 4, 0 is your x-intercept. 0, negative 10 is your y-intercept. Similarly, on this next one, we've got ourselves an x-intercept at 20, 0, because that's where it crosses the x-axis. And we have ourselves a y-intercept at 0, negative 20. Depending on the situation, they may want you to write out the full coordinate just like we did, or they may sometimes just have you list, hey, the x-intercept's at negative 4, with the implied knowledge being that if it's an x-intercept, that means y is 0, or similarly, the y-intercept is negative 10, because the implied knowledge is that that x-coordinate has to be 0. So just pay attention to the formatting that you're supposed to be doing in the problem. We can also graph using intercepts. In particular, that is basically combining your knowledge of, hey, I can find points on a line by plugging in values, and hey, I know specifically some special values are that if we have an x-intercept, that means it crosses the x-axis, and that means y is 0, and if it's a y-intercept, that means it crosses the y-axis, and x is 0. I'm just going to highlight that in 2 different colors here to sort of differentiate those 2 processes. So that's something we can do with an equation in any format. So for example, if you're given this linear equation not in just y equals stuff form, so in that case the more formal name would be Slope-intercept form, something that there's a separate video on, but if it's in this more standard form where we've got coefficients in front of the y's, coefficients in front of the x, nice things to plug in are 0. So in particular, let's say you want to find the x-intercept. You're like, great, that means I make x 0. Plug in 0 for x. That means that whole term cancels to make 0. And then I would just be left with 5y is equal to negative 15, divide by 5 to undo multiplying by 5, and then I get y is negative 3. That's my intercept point. Similarly, if you want to find your x-intercept, you'd say, great, that means y is equal to 0. Plug in 0 for y. That makes that whole term go away. And then whenever you're here at the end, you would say, okay, my only step now is to undo multiplying x by negative 3. I'm left with x is 5. You'll also know that you found an x-intercept because you literally ended up finding x because the y's went away, versus you'll know you were finding a y-intercept because you literally ended up solving for y because the x's went away. Then you can just plot your 2 points and then connect them in a nice, beautiful straight line. So let's practice that method a little bit more. So this solving might involve some fractions, which is fine. Fractions are still numbers. But go ahead and find both your x-intercept and your y-intercept, and then use that knowledge to plot the equation. So pause the video, try it yourself, and then we'll compare. So in particular here, if I want to find my y-intercept, that means I need to plug in x is 0. So I'm going to rewrite my equation. But I will have plugged in, instead of writing x, I'm going to write that x is 0. Anything times 0 is 0, so that ends up canceling out, so to speak. So you're left with negative 2y is equal to positive 6. Now as a last step, I need to undo multiplying by negative 2, which I would undo by dividing both sides by negative 2. So then y equals 6 divided by negative 2 is negative 3, and my full coordinate would be 0, negative 3. Similarly, I can also find the x-intercept by rewriting the equation, but everywhere I see a y, plugging in 0. Anything times 0 is 0, so that's going to go ahead and cancel out to make 0. And then I would still be left with 2/3 x is equal to 6. I'm going to choose to do this with 2 different parts of inverse operations. So first I'm going to undo dividing by 3 by multiplying both sides by 3. I would be left with 2x is equal to 6 times 3 is 18. Then I'm going to undo multiplying by 2 by dividing by 2. And I would be left with x is equal to 9. So my x-intercept would be at 9, 0 because I had just plugged in 0 for y. Then I can plot both points. So I have 9, 0 over here, right 9, up and down 0. 0, negative 3 down here. Left and right 0, down 3. And then I can connect these in a nice, beautiful straight line, and I've plotted my equation. And plugging in points, and in particular finding intercepts, is a valid way of graphing any equations, and is also in particular very reliable for linear equations because they are always going to have both an x and y intercept.